Check if the equation 1 over x times dy dx equals 2y plus 3 is separable. If it is, solve it. An equation is separable if I can write all the variables of one type on one side and the variables of a different type on the other side. So what I mean by that is if I can write all the x variables and the dx on one side and all the y's and dy on the other side. So let's try to do that. If I'm going to multiply both sides by x dx, I get dy equals 2y plus 3 times x dx. And then if I divide both sides by 2y plus 3, I get 1 over 2y plus 3 dy equals x dx. So yes, I was able to actually have all the variables, all y variables on one side and their differentials, and the x and dx on the other side. So when I have that, the next step is to integrate both sides. So I'm going to integrate the right hand side with respect to x and the left hand side with respect to y. So in order to solve the left hand side, we can use substitution. You can say u equals 2y plus 3, du equals 2 dy. So I need to have a 2 up here. So I have the 2 dy to make it du. So when I multiply by 2, I multiply by 1/2, so that I have like multiplying by 1. So on the left hand side we get 1 over 2 integral of du over u equals, on the right hand side it's pretty clear, x squared plus some constant. So on the left hand side it's 1 over 2 ln of absolute value of u, but I'm just going to substitute it back here. I'm going to get plus some constant, let me call it constant 1, and then plus some constant on the other side. So what I'm going to do is I'm going to move this constant on the right hand side, and I'm going to explain this one time because I'm just not going to use it in future videos. C minus C1, it's a constant minus another constant, which is also a constant. So I'm just going to use plus C to represent that subtraction of two constants. So then we multiply by 2 both sides, and I get the ln of absolute value of 2y plus 3 equals x squared plus 2c. Again, 2 times a constant. C is still a constant, so I'm going to keep it like that. If I leave the solution in this form, this is called implicit solution. So if the solution has to be written implicitly, I can leave it like this. But I can move further and try to write my solution in explicit form, which means to write the dependent variable in terms of the independent ones. And in our case, we have dy dx, so the independent variable is x and the dependent one is y, so I want to write y by itself. So what I'm going to do is I'm going to raise everything to e. So e to ln is going to give me absolute value of 2y plus 3, and the right hand side is going to be e to x squared plus c, or e to x squared times e to c, which again, it's a constant. So 2y plus 3 is plus minus c e to x squared, so I just open the absolute value. Again, the plus minus c is going to be some constant, 2y plus 3, and to get y by itself, I'm just going to subtract 3 from both sides and divide by 2, and again, c divided by 2 is a constant, so we end up with y of x is c e to x squared minus 3 over 2, which is explicit solution. if you are wondering how many solutions basically this differential equation has, well, it has infinitely many because c, it's a constant. So for any constant, so for any value you give to c, you are producing another solution. So, but do we have any unique solutions? Well, if our initial equation, so dy dx, which was equal to, so we had 1 over x times dy dx equals 2y plus 3. If we had an initial condition, like for example y of 0 equals 4, then we would be able to calculate the constant. So how do we do that? If we replace y of 0 into the solution, let's put it in a box to remember it, that this is our solution, we get c times e to 0 minus 3 over 2 equals 4. So c minus 3 over 2 equals 4. C equals 4 plus 3 over 2. So c equals 11 over 2. So our final solution is 11 over 2 e to x squared minus 3 over 2, a unique solution. I hope this helps.